Today we will learn how to apply ADF test or ADF unit root test, or in other words augmented Dickey folder unit root test on a set of data here. I have chosen a data set or series with more than 2000 observations, so it's 2355 observations to demonstrate the application of ADF test on variable. Now, before we go to the technical side or to the estimation side of the model, ADF model, I'd like to draw the graph of this series and see or do an eye examination of any pattern or anything that might catch or might be important in my assumptions, or in my assumptions that I will have to make in my ADF test later. So I'll go to do the graphing. I'll go to view, I'll choose graph, and I want line, so that's the first one. Okay, now this is an exchange rate, or it's the logarithm of exchange rate series, and this is the US dollar to euro exchange rate, consisting of 2355 data points or observations, so all of them here. Now this is the graph of the series, and as you could see, we have a trend in our series. In other words, the observations trend upwards, or series trend upwards as time passes. So it is important that we include a time trend in our model, in our ADF model later. At the same time, we could include a constant as well, because the series data generating process, this process doesn't evolve around a zero mean. In other words, if you put a line here, the series do not sort of fluctuate around that line. It actually fluctuates around something else. Like if you put a line here, so that's what it fluctuates. So it goes down and up around this line. Also, in other words, it moves around the sample average of non-zero values. So whatever value, the average of the sample basically is this value somewhere here. You could test that as well. You can find the average of this sample, like if you go back to spreadsheet value. So if the average of this sample is something like, I would say 1.15, could be a little higher, so it could be 1. Let's say 20. In that case, if you go back to graph again, so if we assume that the average of the whole sample is 0.2, then if you put a line around here, as you can see, the series evolve around that line. Actually, it goes down below that line and goes and up that line, so it crosses it and comes back probably later. So that means the sample series evolve around a constant. So in our unit root test, we should include a constant as well. In case the pattern doesn't evolve around the constant but evolves around this zero mean, like goes down, up and down, but doesn't go far away from the line, zero line, then that we don't have to include a constant, or we don't have to include a trend as well. Now this is the characteristics of our data. So there is a trend here which is moving up. So if you put a trend here, line here like this, the data is evolving around the trend timeline. So at the same time, it's also evolving around the mean. So in fact, our model is random walk with drift and time trend. We would have purely random walk if we didn't have any of these, like constant, if you didn't have any sort of average, constant average, and then a trend. Like the random walk on its own is like the one that moves around zero only. So let's go now and check this, and these are the assumptions basically. So we know that we need a trend, we also need a constant. So let's do that and then see if really our assumptions are true. and really if this is actually stationary or non-stationary. In other words, the purpose is to see if the data is stationary or non-stationary. Stationary means the series evolve around a constant mean. Here I can see that it's not constant, it's going up and at the same time going up and down here, so it doesn't evolve around a constant mean. So let's go to view. Right, let's go back to spreadsheet just in case. You usually don't have to go back, and here is data. We will now analyze this data now. So we go to view, go to unit root test and Augmented Dickey full test, and here are others as well. We will come back to these later. I will explain them in some other videos, but today the easiest and mostly used one, Augmented Dickey full test, even though it has been criticized so much. Now what we want is to leave the test, to do the test in level. In other words, we will not difference the we will not difference the variable. In other words, we will not difference the series. We will leave it as in levels. So we will keep it as this. Now we will go to the second section here. In this section we will have to choose now one of the three here. Now as we said, we need an intercept, so we can have that, but we also need a trend as well, trend and intercept, and we don't need anything here. We don't need none basically. In other words, we discovered that it's not random walk, purely random. It's random walk with drift, which is intercept, and the time trend, so we need to choose this one. But I will come back to these two as well and choose them and show you that why we have chosen this. Now lag length, there might be a question how many lags to include there. We will let SBC or Schwarz info criterion to choose that, or you can let AKK information criterion or Hanan Queen criterion or any others here, modified ones as well. So let's leave it as it is. So Schwarz criterion, maximum lag length 26. It's up to you to include, but if you have, let's say, daily series, it's better to have higher, but it automatically does it. You see, we have more than 2000 series, so just choose this automatically to 26. But if you have monthly series, maybe you change it to 12. But you can also specify it yourself. Let's say I can fix this lag by saying you can include a 12 here, and then it automatically so includes 12 series, no more than 12 or no less than 12. But I would rather leave it to this criterion to choose it for me as an optimal value, so I'll leave it as 26 value as well. Now once we specified and made our assumptions, I'll press OK. Now here is the ADF unit root test output. Right, interestingly, what happens is, this is the hypothesis test area. We will leave it for now. Interestingly, we didn't have any lag here, so Schwarz info criterion didn't choose any lag for us, so maybe this is the optimal parsimonious model for us, so they prefers that way. So now what is important here is, let's look at the variable regression itself here and the coefficients. Now this is our null hypothesis here. Well, null hypothesis is that lnx has a unit root. lnx has a unit root, and to find out whether it has or not, we run this model, and the dependent variable is difference of lnx, which is regressed on lnx first lag, c, which is constant, and trend. Now here are the coefficients of each of the regressors, and standard errors and t-stats, and probability values. As you know, if these values are less than 0.05, it is sort of highly significant, and in research many researchers choose 0.05 as a benchmark rather than 0.01 or 0.10. That is sort of strong indication of significant. But if you could also go with 0.10 as well. That's weakly sort of significant usually in practice. Now very interestingly, look at the value. This is an important thing here. Is this significant? Yes, it is. It is significant at 5% level, even at 1% level. Now second interesting point is here, C. Is this significant? Yes, so we didn't make any mistake in choosing C, in including C in our regression, so it's a good thing. Is this significant? Yes, so trend also is a significant value, so we didn't also make any mistake or erroneous assumptions in the earlier stage when we did this test. Now if you look at the t-statistics of our lnx, it is minus 3.026490, which is the same as this t-statistics. And in this test we ignore the probability values here because this coefficient is not distributed normally. In other words, doesn't follow t distribution, is not distributed, it's not t-shaped distributed. Basically these coefficients should be compared to the sort of the t-stats of these coefficients should be compared. These t-stats should be compared not against the t-stat itself, but against the critical values tabulated by Dickey and Fuller. Now I'll show you that one. Now here it is. Here is the table. You can actually download this from on Google. That's what I did. These are the critical values for augmented Dickey Fuller test. Here they are. Now we have included constant and trend, and also what we have is more than 500 observations. We have 2000 something observations. So now at 1%, our critical value that if we compare our t-stat is minus 3.96, which is, if you look at this here, is the same as this one. Okay, let's move. Yeah, so at 1% it's this value. Now at 5% it is 3.41, so it's this one, and at 10% level it is this one. Now these critical values, that basically we compare the t-stat of the coefficient here, lnx, which is this one, against the critical values from this table. Now to make it easier, the e-views shows the critical values here, so you don't have to look at the table as I showed you earlier, but it's just for something, it's something that you could actually learn from. In other words, I'm just trying to say that don't take these values. Usually you go by this table and you go by these t-stats. So these are the ones that you compare. Now what we need to see is this one has to be greater than these in absolute values, so it has to be greater than these in absolute value. In that case we will reject the existence of unitary test. In other words, our data will be stationary. But in this case the absolute value is 3.02, which is smaller than 3.12, even the weak significant, not even weak significant level, so not even at 10%, so you don't have to look at further. Now that can be tested here as well. It's 12%. There's a 12% chance that we made an error, we could make an error by estimating this, so it's a highly significant, non-significant value basically. Now what we do, what this means now, this means that in levels, in other words, these values in levels are not stationary, or they do not evolve around a zero mean in levels. So what you do, you go back again, unit root, and this time we will see if in first difference our series become stationary. Now we will keep the lag length selection criterion unchanged, and we will keep trend and intercept because they are significant, and press OK. Now what we see here is the coefficient is near to, well, near to -1 here, but we will ignore that for now. However, what is important is this value t-stat, highly significant, but we are not going by these probability values of t-stats. Now we are going by these critical values, and here is the same value here. Now this value in absolute terms, like 48.47, is great, much greater than the 3.96. So we have an evidence that the series L and X is stationary when we take the first difference of the series. So they are stationary in first difference, not in levels. So that's what we found now. Now interestingly, this will be interesting actually to say here. Let me show you something here. What this is this. What we estimated here is the Dickey Fuller test works like this. Augmented Dickey Fuller test. D stands for difference. So difference of L and X was equal to what? It was equal to, we included constant plus trend plus, and we have ln x itself, and plus an error, usually error. Now this is the Augmented Dickey Fuller test model, or the model itself here, when we estimated this in levels. In other words, if you go back to unit root test and keep it as levels and press OK, this is the equation I estimated basically here. This is the equation. Sorry, this has to be in minus, so I missed that point here. -1. Okay, ln x, I put the trend as well here. Now we are looking at the coefficient of this value here, and the hypothesis is that the coefficient of this is equal to 0. In other words, ln x has a unit root test. Now, as we found here, we failed to reject that thing, and we estimated the second. We did the first difference model. Now, in that case, what we did is we estimated this again, the same model, but in the second difference it twice basically, and at this point we put this d value here, which means we differences the one time lag as well, one period lag as well. So that's the second model we estimated, and we compared the coefficient of this variable against the t values, sorry, not coefficient, the t stat of this coefficient, which is this one, against the critical values tabulated by Augmented, Dickey and Fuller basically. So now we found that the series is stationary in first difference, not in levels. Now I want to go back, and as I said earlier, I want to now include intercept only without trend and estimate the same model for the first difference and press OK. You see, constant on its own is not significant, and you can still see that the series is stationary because it's in first difference as we found earlier, but this is not significant, so there is no point in including it if it's not significant. However, let's go back again, and we will do, since it says not significant, you can drop this constant from the equation. So I'll go to none and estimate it. Again, it's good. So we rejected this hypothesis as it is, as it was shown before, but we didn't include any constant and trend. However, it's best always to estimate the model including intercept, including both intercept and trend, and none as well, and choose intercept only if the intercept term is significant here, as I showed you, but it's not significant, so you don't have to include it. So go back and then estimate the trend and intercept included, and see if it's this time significant. Now you can see that the C is not that significant, however trend is significant, so you can't include trend on its own without C, so you can't drop C and include trend, so you have to keep it there. But however, in case you have both C and trend non-significant, just go back and estimate none, don't include any and just estimate. But in our case, since trend is significant, sorry, I'll go back. Since trend is trend is significant, we will have to include C because it's in the model intrinsically, or it's modeled like this. The test is modeled like this by the authors Dickey and Fuller. Okay, now with this we could end this the model estimation for unit roots, but I would like to test whether this series as we found is stationary when we take the first difference. So how to do that? In levels, as you can see, it's not stationary, and that was proved by the Augmented Dickey Fuller test. Now the test told us to difference it in our regression. So you shouldn't, in other words, the test says you shouldn't include levels of this variable, but include in the first difference in your model. So whenever you are regressing something on ln x, then first difference it first and then regress it. Otherwise you get a spurious regression or nonsense regression, or your model will not be sort of acceptable. Now you don't get in some cases you mightn't get blue coefficients. Now what I want to say here is I want to first differentiate and show you whether this is stationary or not, the ln x is stationary or not. So how do you do this? We go to generate. How do you do that? Quick, generate series. Now d ln x is equal to first difference of ln x. Okay, now d ln x. Now here is the first difference of these values, the series ln x. Now I want to graph it now. Okay, now as you can see, the level variable in first difference becomes stationary. In other words, it has now the mean of this data processing generating process is actually 0. So if you put a line across here, the values go up and down that line. But in this case, if you put a line across 0 or along 0 or on 0 on y-axis, you will see that the values actually do not come back to 0. They do not come back to 0 line. So they go up or down. They're sort of drifting. Now in this case, the values go up, but they come back quickly to 0. So this is the stationary series, while this is not stationary series. As this characteristic, as you can see here, is that the model has a trend and at the same time non-zero mean. So it could be somewhere here, the mean could be somewhere here, or a little bit lower than that. So now this is the demonstration of how to apply unit root tests, namely the Augmented Dickey Fuller test. I will make more videos on other tests, because the unit root augmented ADF test has some power problems. In other words, when you have structural breaks in your data, it's best not to rely on this data test on its own. You could do a range of unit root tests before making any regressions or assumptions. So I hope you will find it useful, and hopefully you will leave feedback, and so that next videos will be improved according to your feedback. See you next time then.